Thank you, everybody, for coming. For those of you who don't know Jeff Groah, he teaches math here at Lone Star, and he also collects coins, which is really amazing. He's been a supporter of CAC for as long as I've known CAC's existence, and he's currently on the committee that keeps CAC afloat. So, Jeff, welcome.
Thank you.
That's it.
History of Big Bang. Actually, this does pertain to my dissertation, where I proved the first shockwave existence theory for conformally flat spacetimes from Big Bang until Big Crunch.
Say what?
That was my dissertation. You can see here I have the Hubble deep field as the background. Just about every object that you see here is a galaxy. So, for instance, a galaxy like this might be similar in size to the Milky Way. The Milky Way has between 100 billion and 400 billion stars. A lot of stars. Each of those might have hundreds of billions of stars, and some of them trillions of stars. So, yeah, where did it all come from? Well, the term Big Bang comes from Fred Hoyle. And he invented this during a 1949 BBC broadcast. More on this later. So that's where the term comes from. But the ideas behind it come from this guy, Albert Einstein, who in November 1915 had 4 general relativity papers. The third had his calculation of the orbit of the planet Mercury, resolving a long-standing problem of the orbit of Mercury. The French astronomer Leverrier had discovered that Mercury doesn't follow the path predicted by Newton's theory of gravity, so he thought it was being pulled off by some planet. And since it's Mercury, it has to be some planet really close to the sun, so close to the sun that it must have been really hot, and no one had ever observed it because you have to look right at the sun to see it. And so it must be really hot. It has to be called Vulcan, the planet Vulcan. So that was Leverrier. He launched the hunt for the planet Vulcan, which lasted until Einstein, and Einstein said, okay, all of those observational errors of Leverrier are explained by the wrong theory of gravity. If you choose Einstein's theory of gravity, you get it right. Okay. And so that was his third paper of the month. The fourth paper included his field equations. And so there's also a paper that he submitted in March of 1916. We'll look at that in a minute. Actually, right now, this is the paper in German, and this, how about the English? You can see he's talking about the planet Mercury in here. Laws of motion, planet Mercury, and the 43 seconds of angle per 100 Earth years that this perihelion shift was off. Very, very small, but it amounts to some minutes in the transit of Mercury across the sun. So it's well within observational errors from even the 1860s, when it was first observed by Leverrier, right here. Well, he explains it with his theory of gravity. So that was Einstein's third paper. The fourth modeled gravity as curvature, his famous field equations. We all know that in 1919, Sir Arthur Eddington actually took an expedition and took camera images of stars near the sun during a solar eclipse. The only time you can take pictures of stars near the sun. And he, through careful measurements, was able to show that these positions of these stars, the light had to have bent around the sun, so they appear a little bit farther out from the sun than they actually were, because their light is bending around the sun, because of Einstein's theory of gravity saying that gravity is not an just a weird acceleration. Gravity is a bending of space-time. Changing the shape of space, and so light will curve on that bent space. It'll appear to be farther. The stars will appear to be farther out from the sun than they really are. And this was observed by Sir Arthur Eddington in 1919. So there's a lot of other good evidences for Einstein's general theory of relativity, his theory of gravity. Gravity is not a force. Gravity is the bending of space-time. The most recent one would be the gravity probe B. Anyone here know of gravity probe B? It was just a decade ago. And it was a satellite in polar orbit around the Earth, and they had the most accurate gyroscopes known to humankind. These things, the spin axes are all aligned, they're all pointing at a particular star. they should stay in that orientation if Newton's theory of gravity is right. But if Einstein's theory of gravity is right, then the Earth will bend into the space around it and cause the spin axes to fall short a little bit. And it's measurable over time, and that was measured by gravity. In addition to another effect, the turning of the Earth twists space-time a little bit, which causes this frame dragging effect, which was also measured by gravity. So Einstein's theory is predicting things that never would have been imaginable under Newton and his theory of gravity. And so it's actually the best theory of gravity that we have for things that at least happen inside of the solar system. Okay. So check out the date of this paper, 13th of January 1960. This is by Kurt Schwarzschild. And this is January of 1960. This is 2 months, less than 2 months, after Einstein publishes his general theory of relativity, right? A month and a half or so. And Schwarzschild comes up with the first solution to Einstein's field equations in January of 1916. Look at his death date, 11th of May 1916.
Oh, wow.
He died of illness during World War I as an officer, but he didn't live very long after this paper. He must have been ill at the time when he published this. But the interesting thing about Schwarzschild's exact solution to the Einstein field equations is that it has a black hole. The very first known solution has a black hole. So what did people think? You can show that the Schwarzschild solution is the only spherically symmetric, asymptotically flat, so that gravity gets less and less as you go out, empty space solution to the Einstein equations. Okay. So it will be the gravitational field outside of an object that's massive but not spinning. The spinning solution would be the Kerr solution, which was found in 1964. But 1916, Schwarzschild comes up with this black hole solution, so everyone thought this is nuts. This just shows Einstein's theory is way off base. How could it have a black hole, right? Until 1939 with the Oppenheimer-Schneider solution to the Einstein equations, which modeled a massive dust, which is a pressureless fluid, collapsing and forming the Schwarzschild black hole. So after that, people thought, well, maybe stars really can form black holes. You recognize this from movies, Gargantua, black hole. Don't recognize that? All right. So, however, it was soon discovered that Einstein's equations make the universe non-static. In other words, masses attract other masses, right? And since masses are proportional to the curvature of space, space is going to attract space too. Okay? And so if you start out just sitting there, eventually space is going to contract in on itself and the whole universe is going to disappear at a big crunch. Okay? In finite time. Yeah. The universe should collapse in on itself, and so Einstein's thinking, well, we can't have that. If the universe starts out not expanding or contracting, then it will contract and eventually vanish in a big crunch. So here's a big crunch. I've taken that Hubble deep field and I've wrapped it using an app that I found online, wrapped it around a sphere, and now we have this animation of the whole universe disappearing in a big crunch. Okay. So there's your big crunch for you. So if the universe is expanding, then it should have started in a big bang. Right? If it's expanding, it had to have started somehow. And so expanding spaces should expand at slower and slower rates due to self-attraction, which is opposite what was observed in the 1990s, right? That the space seems to be accelerating away. So here's the Big Bang. Ooh, the universe, do you want to see that again? Here's the Big Bang. The universe coming up from nothing, right? Okay. So, if space should ever stop expanding, it must collapse in on itself in finite time. So if space is expanding now, it's possible that it will stop expanding at some point and then collapse and form a big crunch in the future. So that's possible. So here's a Big Bang and a big crunch, bang followed by a big crunch. Okay. That's a possible fate of the universe. So The implications of Einstein's theory of gravity are, the end design, there's going to be a big crunch in finite time. The universe will disappear. The universe had a beginning or both. Okay, those are the options. The universe coming into existence violates conservation of mass, energy, and momentum. Right? In fact, not only did mass, energy, and momentum come into existence at the time of the Big Bang, but so did space, and so did time. Okay, so time, space, mass, energy, momentum all had a start at the Big Bang, if such a thing exists. So here's a model that I thought of. Suppose you have an empty space just sitting there. Empty space would just sit there, not expand, not contract, just sit there. And I'm going to hit it with what I call a delta function pulse here, a delta function force. And I'm kicking, it's like kicking the universe and making it expand and creating all mass, energy, and momentum at that time. So with this one pulse, boom, universe expands. But then you think to yourself, if all mass, energy, and momentum was created at this one point, why do you need an empty universe sitting around? Why not bring that point of creation all the way back to the point of the Big Bang? You can still model it. Most cosmologists only model the universe for times greater than 0. But it's possible to include t equals 0 if you include this delta function source. But doing so violates conservation of mass and energy. So a Big Bang requires an appeal to non-mechanical, you can't have all mechanical elements coming into existence by mechanical elements. It has to be something external to that. Okay. So all space, time, mass, energy, momentum brought everything in existence through non-mechanical, non-physical forces. So a Big Bang requires that. What do I say? The Big Bang is the ultimate non-conservation. And that brings up the question in the beginning, right? We've all seen this, Genesis 1:1. And this is the problem that physicists had. None of them wanted to believe Genesis 1:1, right? So this, by the way, is 8th February 1917. Einstein introduces the cosmological constant in order to keep the universe static. He shouldn't have done that. Here it is, that lambda right there, that's the cosmological constant. And this is his paper. This is actually his paper from February of 1917. Why did he introduce the cosmological constant? Because if you exactly tune the cosmological constant to a specific value, you can make the universe so it won't expand or contract. It'll just sit there and have existed since eternity. Right? Now, that was the goal, is to have a static universe so that you avoid all these ugly issues about non-conservation and whatnot. But there it is, Einstein's paper, 1917, the cosmological constant brought in. So, without the cosmological constant exactly tuned, the universe is not static. With the cosmological constant, the universe is unstable. Small variations in that cosmological constant will cause the universe to either expand or to contract. Okay, so you can get a Big Bang or a big crunch, one or the other. So the universe will expand or contract. Einstein said, since I introduced this term, cosmological constant, I had always a bad conscience. I'm unable to believe that such an ugly thing is actually realized in nature. So by 1921, people are looking for other solutions to this issue. Okay. So you have Weil producing his unified field theories, and Eddington, what he leveraged off of Weil's theory to create his own theory, unified field theory. And so you have these guys. All right, illustrating the Big Bang and the time vector field. Let's suppose that the spatial part of the universe is a circle. Now, that circle, if the universe is expanding, that circle should get bigger. Okay? So I've illustrated that by this kind of weird surface here, starting out at a Big Bang here. But the universe expanding in maybe a slower rate because gravity attracts, it'll slow down the rate of expansion according to the traditional cosmologies. The time vector field is tangent to that surface, pointing in the direction that the space is expanded. That's how the time vector field is modeled in here. So as the time goes by, you can see that space will expand, and these vectors, the time vector field, will be still tangent to the surface, but just farther out, still pointing in the direction the space is expanded. Well, what about earlier in time? How far can you trace these time vector fields back? Is there a limit to how far you can trace these time vector fields back? You have the time vector field pointing out here. Notice that it's becoming more and more divergent. And at the Big Bang, it'll have infinite divergence. You can't extend the time vector field. Here's a divergent vector field. The vector's all pointing out. Okay? Here's a convergent vector field. All the vectors pointing in. The problem you have is when you bring these time vector fields back towards the origin, you can't continuously extend it any further back than t equals 0. So you can't extend time any earlier than the Big Bang. In other words, time has no meaning. Earlier than the Big Bang, there's no earlier. There's no time. Time didn't even exist. That's the implication here. At the Big Bang, all those time vector fields are pointing out at that same point. You can't extend time any further out, any further than t equals 0. Okay. All right. Here's the cosmological argument. Everything that has a beginning has a cause. The universe had a beginning. Therefore, classic syllogism, therefore the universe has a cause. What that cause is, we're not saying we had to have had a cause, and it has to be a non-material cause. It's outside of time and space, so it's an uncaused cause. And it's also timeless, whatever that cause is, because it's outside of time. Timeless, causeless, immaterial. So whatever you appeal to as the cause of the universe must be outside of space, time, mass, energy, and momentum. In other words, the cause of the universe is outside of all known physics and mechanics. Good. Not of all known physics. All of it. So choose your favorite.
Well, you got the word known.
That's right.
The get out of jail free card.
So quantum fluctuations, that's just an unscientific method. So are bubble universes. And all those modern inventions that we've tried to invent to explain the Big Bang, there's no science to it. Nothing can be observed. It's not possible. Okay, back to the history of the Big Bang. 1922, you have Alexander Friedmann, a Russian, who solves the Einstein equations for a homogeneous isotropic mass. So it's homogeneous, so mass is spread uniformly throughout the universe. It's isotropic, so it'll look the same in all directions. No matter which way you look, it's going to be looking pretty much the same. And what he finds is there are actually three solutions that he found. One for the spatial cross-section of the universe being flat. One for the spatial cross-section of the universe being having positive curvature, and one with negative curvature. So we found three solutions: curvature 0, curvature positive, curvature negative. And he did this in 1922. Okay, but check it out. He didn't live very long beyond that. So he found these three solutions. He published his famous Friedmann equation governing the rate of universal expansion, but all of his solutions have a Big Bang. And the spatial cross-section having positive curvature also has a big crunch. Both a Big Bang and a big crunch for that particular part. What are his disadvantages? Well, he was Russian during early phases of the Soviet Revolution, right? You can imagine how difficult it would be to be an intellectual at the time in Russia. But also, he died young, so he didn't have time to promulgate his particular theories. In 1923, Sir Arthur Eddington published Slipher's data from 1922, Lowell Observatory, showing that most galaxies, spiral nebula, are receding on average 600 kilometers per second from us, which is pretty fast. 600 kilometers per second. Yes. So he doesn't give distances to each galaxy, so he can't give a Hubble relation. He didn't calculate the distances to these galaxies. That was left for later. Georges Lemaitre, he, 1927, rediscovers the Friedmann solution to the Einstein equations to start promulgating this idea of the Big Bang. But even he had problems. First of all, well, he did predict the Hubble relation. He had his disadvantages. He was Belgian. Okay, so he's outside of the usual course of these big universities. He's a priest. His publication was in an obscure publication, and he's quite young. So he actually met Einstein. Einstein didn't take him seriously because he's so young, and he didn't like his theories anyway, because of the Big Bang. Right? Einstein's still trying to avoid that. Lemaitre, he also followed suit in his paper. This is taken from his paper in 1927. He's using this lambda. That was the cosmological constant. He's trying to avoid a Big Bang, even in 1927. Okay. The only one who's not avoided that so far is Friedmann. Okay. So we'll recognize Edwin Hubble here. He showed that spiral nebula are individual galaxies. He resolved with his big 100-inch telescope individual stars in these galaxies, distant galaxies. But he did more than that. He showed a linear relationship between distance and recessional velocity. And I'll show you that data in a minute. January 1931, Einstein visits Hubble at the Wilson Observatory, and Einstein had a look through his 100-inch Hooker telescope. This is the Hubble data. And I've taken the liberty of plotting that data and giving you a least squares line of best fit, a line of regression, and calculated the correlation. You can see then that this is the distance and this is the velocity, the recessional velocities. Slipher was averaging around this 600 kilometer per second point. As you can see, the recessional velocities get higher and higher as you go out. So that's the actual data that this was based on. Why are they dancing around this line? Because galaxies really are, some of them moving towards us, some of them moving away. Why do they seem to be more and more redshifted as they go out, more and more Doppler redshift? It's because the galaxies are just sitting there in a universe that's just expanding. The longer the light has to go in transit, the longer that space expands and stretches the light waves out, redshifting them more and more. And so the galaxies that are further away will be more highly redshifted just because the universe is stretching apart. Good evidence for a Big Bang, right? So you have Robertson and Walker in the late 20s, early 30s. They start promulgating this actual Big Bang model, okay, using the, it's now called the Friedmann-Lemaitre Robertson-Walker Big Bang cosmology. Okay, after those four guys. 31, Lemaitre predicts the early universe may be observable as cosmic ray radiation, which is wrong. It's actually microwave radiation. 34, Richard Tolman showed expanding universe would cool black body radiation. So he's already predicting the cosmic microwave background radiation in 1934. Okay, that's Tolman. Robertson and Walker descended and developed the theory of Friedmann, Lemaitre, as well as Robertson's earlier work. In 1948, Ralph Alpher, Robert Herman made the first prediction of the cosmic microwave radiation, estimating it to be 5 degrees Kelvin, which is a little bit off, but you can't blame them too much because the astronomical data was limited. 1949, the term Big Bang was invented by Fred Hoyle during a BBC broadcast. It was intended to be pejorative. It's a Big Bang. Big Bang. Okay. His tone was insulting. He preferred his steady state theory. Well, we know the Big Bang theory violates conservation of mass energy momentum, but so does the steady state theory, because he posits a continual creation of mass energy and momentum over time. So he's violating conservation, just spread out over large periods of time. Okay. And so that was his way of avoiding a Big Bang. But he still violated conservation. So he believed that having a beginning for the universe smacked of creation. And he said, the reason why scientists like the Big Bang is because they are overshadowed by the book of Genesis. It is deep within the psyche of most scientists to believe in the first page of Genesis.
Really?
Yes.
Who proved that?
Now you know. That was Fred Hoyle,
Okay.
who later had a change of heart. Not read too much into his statement in 1949. Einstein's biggest mistake. In 1956, George Gamow said that Einstein remarked to me many years ago that the cosmic repulsion idea, as cosmological constant, was the biggest blunder he had made in his entire life. His entire life. In 1917, he makes his biggest blunder, according to George Gamow. John Archibald Wheeler said, quote, going into the doorway of the Institute for Advanced Studies Fold Hall, well, Einstein visited that in the early 1930s. Einstein and George Gamow, I heard Einstein say to Gamow about the cosmological constant, that was my biggest blunder of my life. And a third quote, Ralph Alpher, in conversation with Einstein at Princeton, where Einstein spent most of his time in the US, concerning the apparent time span of cosmic expansion. A way to fix this was to reactivate the cosmological constant. Einstein did not like this very much. And as I recall, said his introduction to the concept in his early work was a blunder. Okay. So, cosmological constant, don't do it. But just about all cosmologists today still use this cosmological constant. By mid-1950s when he died in 1955, he's using non-Riemannian geometry. His early work was Riemannian geometry. He has four-field equations, he has equations of motion, he has a gravitational function, not a gravitational constant. It's no longer a gravitational constant, it's gravitational, and it's no longer a cosmological constant, it's now a cosmological function. So by the 50s, he's already translated into something completely different, which never caught on, his unified field theory. There's a great book by Václav Hlaváček titled The Geometry of Einstein's Unified Field Theory. It goes into great detail in the whole thing. So, the cosmic microwave background radiation. Well, the more compressed the universe is, the hotter it's going to be. Just like if you compress air in a tire, it gets hot, right? At an early epoch of the universe, there was light and matter, but matter was so hot that it could not form atoms. There could only be a plasma. Some early state of the universe is so hot. In such a scenario, light, being electromagnetic, cannot travel freely. It bounces everywhere. Okay, it's scattered. Okay. Light is scattered. Light cannot freely travel across the universe. Not until the point when the universe is expanded enough to cool enough to form atoms that light can freely travel across large distances of the universe. And that's the cosmic microwave background radiation that has been so stretched out that it's now shifted from light rays to the infrared, to the microwave into the spectrum. So it now has a temperature of 2.725 Kelvin. And so it's because of that earlier epoch of the universe, there's an earliest time beyond which observations cannot be made of light. Light cannot be observed any earlier than that time of absolute scattering. Okay? There's an impenetrable wall. No observations of light can be made through. The only things you can see from an earlier period might be gravity waves, if there are any gravity waves that formed at the creation of the universe somehow. Some primordial gravity waves, maybe this could be detected, but no one's ever detected it. Or maybe neutrinos might be observable from an earlier epoch. But there's a kind of impenetrable boundary any photographic light evidence, you can't observe anything beyond that. And these are Penzias and Wilson using this microwave antenna back in 1964. They discovered the microwave background radiation. And they pointed this thing in all different directions, and you get the same radiation from all different directions. And this is the leftover of the Big Bang. Okay. This microwave background radiation. It's the leftover from that earlier highly condensed state of the universe. So whatever happened to the universe earlier in time, it definitely was more compressed in the past. And we see direct evidence of that in the microwave background radiation.
Was this at Lowell Observatory?
No. No, they were in, I think, New Jersey. And the Lowell Observatory is down in Southern California. Oh, the Lowell Observatory, that's in
Flagstaff.
Flagstaff. Stephen Hawking, 1964 to 1973, he proves, as part of his dissertation in 1964, he proves one of his famous singularity theorems. Now, remember the Friedman, Lemaitre, Robertson, Walker, Big Bang cosmology? They've assumed that mass is uniformly spread throughout the universe, it's homogeneous, and it's isotropic. And so they have three possible scenarios for a Big Bang that arise from those assumptions. Well, Hawking doesn't make those assumptions, but he shows that if you assume that gravity attracts on average, which I guess is a pretty generous assumption, and if you assume that some spatial cross-section of the universe is currently expanding, then there had to have been a Big Bang. There had to have been time incomplete paths going into the past. You have these time paths that terminate where the universe has these singularities in the past. So his singularity theorem proves, essentially, you had to have a Big Bang. The universe is expanding. We know this. Edwin Hubble's observations. The universe is expanding. We have the cosmic microwave background radiation, the heat left over from the formation of the early state of the universe. And he says, okay, if that's true, there had to have been a Big Bang. So this is a big generalization of the Friedman, Lemaitre, Robertson, Walker theory, because he's not making all the assumptions that they make, but he's proving the existence of this Big Bang. Alan Guth, 1979, in an attempt to join quantum theory with general relativity, he creates his inflationary cosmology, complete with inflaton fields. Okay. So he causes, this theory causes the universe to expand very rapidly initially, so that any variations in density of the early matter of the universe would be spread out very quickly, and it'd be very uniform, just like we observed with the cosmic microwave background radiation. And so, his attempt leads to an even bigger Bang, because it exploded even more rapidly at the beginning, right? So, today we have eternal chaotic inflationary models and bubble universes and things like this. Okay, but these are all extensions off of this to try to avoid a Big Bang. But nonetheless, we still have very good evidence that the universe was in a much higher, more highly compressed state. We have these theorems that say that there's this Borda-Guth-Vilenkin theorem. This is 2003. And it basically says if you have a universe that has the light and space structure that we expect the universe to have, then whatever the theory of gravity, it's going to have a Big Bang. Okay, so this includes all of the inflationary models. They also have to have a Big Bang. So, the universe that is on average expanding is past incomplete. It's much more general than Hawking's singularity theory, because Hawking assumes some kind of Riemannian geometry. Okay, they're not even assuming that. It's more general and applies to inflationary cosmologies. It says they too have singularities. So the Big Bang seems unavoidable. So whatever has a beginning has a cause. The universe had a beginning. The cause of the universe need not have a cause, since it is external to time and space, okay, as well as matter, energy, and momentum. So the cause of the universe is causeless, timeless, and immaterial. You laugh.
Sir.
It's quite all right.
Slow down.
There it is. History of the Big Bang. Science is not amenable to the study of the origin of the universe. There are limits to what we can observe. A veil exists preventing us from making observations of the Big Bang. If a myth is a theory of origins, which was something I was taught in college, a myth is a theory of origins, then the Big Bang is a myth on the level of every other creation myth. So, in the beginning was the Word. Okay, this is what we're left with. I want to do something that, I want to continue this just for a few more minutes. This is for Janet, who during my last lectures, she threw a bomb right there at the end, and I didn't have time to answer her question. But her question is, what does space curve into? So I thought I'd talk about that. I've actually made a video just on that on my YouTube website. But you can see, here's a curved space. What does it curve into? Well, the answer is nothing. Gravity is represented by metric relations between points on a space-time. So I'm going to illustrate this. I'm going to drag you through some geometry. It's calculated, geometry is calculated from what are called metric relations, at least the intrinsic geometry. So what are the examples? Well, here's a metric on Euclidean flat space, Euclidean plane. The idea here is basically the Pythagorean theorem. We have a small change in x and a small change in y, leading to a small change in this distance here, a little change in distance. How are they related? By the Pythagorean theorem. Okay. This metric gives you Euclidean geometry. In fact, all of Euclidean geometry descends from this metric. Here's the same metric, but in polar coordinates. I want to generalize on this later. So I want to give this to you in polar coordinates. Notice that the change in the angle d theta is 0, then the change in length s, ds, is going to be the same as the change in the radius, because the theta is not changing, you're just moving out radially. So the change in distance will be just a small change in your radial position. If the change in the radius is 0, then you have only this change in angle going on. This little ds is going to be related to the angle d theta by r times d theta, right? ds equals r times d theta. If that term is 0, you can just take the square root and get rid of the squares. And you have the classic formula from trigonometry, s equals r theta. Okay, so this metric also gives you flat Euclidean space, but I want to do something to this metric. I'm going to create something called the Poincare disk, classic from differential geometry. What you do is you take that metric and you multiply it by this function here. Notice that r equals 0 is fine, you just get 4 over 1 if r is 0. But as r approaches 1, that denominator goes to 0. As the denominator goes to 0, this fraction goes to infinity, and these lengths go to infinity as you go towards the circle of radius 1. And so it turns out that this Poincare disk with this metric has what is called negative curvature. I'll illustrate that. Here's the disk. The edge of the disk is actually not part of the universe because those are points at infinity. Okay. But the straightest possible paths under this space with the negative curvature are these arcs of circles that intersect the boundary circle at a right angle. So those are straight paths. You would just try to go straight, you'd follow one of those paths on this bent space. Notice the space is bent, but it's still part of the plane, right? What makes it bent? The metric relations. Illustrating gravity is just metric relations between points in space. It doesn't have to bend into anything, okay? You see what I'm saying here? By the way, here's an M.C. Escher drawing of angels and demons using the Poincare disk for the geometry to create this. That's pretty awesome, isn't it? Yeah, angels and demons. There's all of these angels and demons are exactly the same size. It's just that the metric makes them look good. You know, it's just that that metric will expand them as they go out because of this factor that blows up as you approach the radius of one. Straight paths can also be straight line segments going through the origin. Those are the only other possible straight paths. So on the Poincare desk here I have 3 of these, what are called the geodesic pads. These are straight as possible pads, forming what is called a geodesic triangle. I have these interior angles alpha, beta, and gamma. But think about this. On this triangle, these sides they seem a bit curved. These angles are a bit pinched. Is the angle sum still going to be 180 degrees? It's not going to be, right? It's going to be less. The angle sum of this geodesic triangle will be smaller than 180 degrees. In fact, we have the famous Gauss-Bonnet relation here. The angle sum is equal to pi, or 180 degrees, plus what is called the total curvature. Here's the Gaussian curvature. We're adding that up across the entire triangle up against an area. And that gives you what is called the total curvature. If the curvature is negative, like it is on the Poincare disk, -1, then the angle sum will be less than 180 degrees. If the curvature is positive, you will get more than 180 degrees. And I can illustrate that here with a sphere which has positive curvature. You can see that here I have a geodesic triangle on the sphere. These lines going from the North Pole down to the equator, turning 90 degrees, going along the equator, turning another 90 degrees and going up. I end up with 2 angles that are 90 and then some. So the angle sum is greater than 180 degrees. And this would be the metric relations with a constant radius. That would give you that geometry, a geometry with positive curvature. Okay. Again, geometry is determined by these metric relations. And Einstein's theory is purely geometric, so it's all determined by metric relations. Okay. So, additional resources, I have these. I'll post the PowerPoint display on the CAC website, LSC Montgomery CAC.com, I think. Yeah, it's unusual. It's not .edu, it's .com. Okay, but that brings the presentation to a close. And if there are questions, you can ask.
If you have questions, we have a mic.
Oh yes, there's a mic right here, and you need to speak into the mic so it can be picked up by the camera.
Right here. Question.
Shall I
I have a mic, but
Well, you don't have this mic.
Yeah.
you seem to think that you've proved that it's a myth. But aren't there a lot of people out there that disagree with that? That think that maybe there's an oscillating thing and there's a different answer?
Well, a myth, by my definition,
Yes.
is a theory of origins. And by that definition, it surely is.
You seem
I'm not saying, I'm
You
not
seem
saying
to
it.
be pointing toward whatever it seems a little strange.
It seems strange what I'm saying?
No, I'm just wondering where you're coming from.
There's no science to a universal bounce. People have posited this idea that the universe comes together in a big crunch and then bounces. The problem with that is the laws of thermodynamics say that eventually you're going to run out of usable energy. And the universe could not have had an infinite existence. It should already have come to an end by now. Okay, in a series of smaller and smaller bounces.
We just need new theories.
You think the problem is our theories?
Yes, we haven't understood some different types of theories yet.
So you're saying there may be a mechanical explanation, it's just not part of any mechanics that we know? Or
I
any
just think
physics that
that,
we know?
I don't know the mathematics right now, but it seems like there's a lot of people that disagree with you.
What's there to disagree with? I'm just giving ideas here.
Okay. I'm just creating conversation.
I'm happy for the conversation, that's fine. Yeah, good for the...
5T-1.
I have no idea about T-1. As far as I'm concerned, you can't extend that time vector field any further back than T equals 0. The time vector field has no
It's
continuous
undefined.
extension beyond that. So time ceases to have meaning at the point of the Big Bang.
Nice word.
So Jeff, what I heard was that we either need new observations or new types of math to possibly make a more thorough explanation.
So so you're saying that the answer to our questions is math caused the universe?
No. You would like to think that math causes everything.
No. The universe caused math.
That's right.
Math just causes trouble.
No, really, it can always be ignored.
Carolyn.
I like this one.
Maybe.
Me too.
Other questions?
I think what you need is
Centrifugal.
another group of data. And I'm not too sure, nor is it my job, to determine. There is a certain amount, say, of microwave data, and the microwave data is good. But we should be looking toward other types of data that might give you different perspective.
Like I say, there are many different theories out there right now. Like I said, there's these inflationary models, the bubble universes and whatnot. None of that is scientific. None of it is any relation to anything that can be observed. So it's
That
not
doesn't
science.
mean that there aren't sets of data that would give us a different perspective.
I'd like to see it.
That is not my area. I'm a boring engineer. We know how to take data.
Well, if you've read the book Flatterland,
Oh,
there's
yes.
the famous Hawk King who has the Space-Time Engineering Corporation. So he's an engineer of space-time.
Maybe we just need new tools to make new observations.
Well,
Yeah.
if you're looking for new data, then you generate new tools.
New tools.
We generally, well, that's an engineer speaking, but we generally don't make tools to do nothing we're not too sure they're going to,
Yeah.
because that's a lot of money.
That's it.
The tools are usually designed at the edge of what is observable. They're designed so that, and what's measurable, they're designed so that you have to use statistics to make any distinctions. That's usually where we are in terms of observations. And there's no really good observations right now of anything close to the Big Bang. All we have is the theory, and the theory tells us, like the Lincoln theorem, that even on the most general hypotheses right now, the Big Bang is unavoidable.
The way things are going with AI, we might come up with something.
You're holding out hope that AI will solve our
Seems like AI is solving everything.
cosmological problems.
Scary.
You never know.
I suppose I have a question, just because everyone's been saying, we need new data, we need new data. So my question is just more clarificatory than anything else. The reason, and so just correct me if I'm wrong, but to summarize, one of the reasons that we rely on the mathematic and geometric models is because the cosmic microwave background more or less prevents us from seeing beyond a certain point in time, right?
I wouldn't say that. That's not the reason we rely upon the geometric models. We rely upon the geometric models initially from the 1915 paper of November describing what happens to the planet Mercury. The 1919 paper by Sir Arthur Eddington about bending of light around the sun. Many other validations of this theory, like gravity probe A and gravity probe B. Gravity probe A was in the 1970s, and they launched, it had two identical atomic clocks, one which went into a suborbital path up to about 15,000 miles, and then came down, and the other one stayed on the surface of the Earth, and they measured that the further you get away from massive objects, the time is not as stretched. Mass stretches the time out, so time will run a little bit faster as you go out, a little bit slower because the times are stretched closer to massive objects. This was measured by gravity probe A. Okay. But it goes out to a limit as you go out. There's a limit to which the rate of time will flow as you go out, finite limit. But like I say, Gravity Probe B measured both this geodetic effect and the frame dragging effect for these gyroscopes. And, so that was also one of the latest pieces of data. So those are all geometric. It's using the geometric ideas. They had to use the rotating Kerr solution to get that frame dragging effect for the Gravity Probe B.
So maybe I should clarify, but the reason that it's ultimately geometric, or at least I'm assuming you're claiming that ultimately any description of the Big Bang is geometric in nature rather than based off of more directly empirical data, is because of just basically there's a point of origin beyond which we can't measure time, right?
The reason that it's assumed to be geometric is that Einstein's theory of gravity is geometric.
Okay.
That's the thing. And they only came up with this idea of the Big Bang, what, 1922? With Friedman? Everyone's trying to avoid the Big Crunch by introducing the cosmological constant starting in 1917, right? And so, Einstein's theory is fundamentally geometric. And so his idea is that gravity is the curvature of space, and the amount of stuff in space is directly proportional to the amount of curvature of space. So the more stuff you have, the more bending you have. The more bending you have, the more you can divert matter using the curvature of space. So it's a geometric theory. That's the reason why we're using geometry. Is that Einstein's theory from 1915 was geometry.
I missed a few semesters in this. So why is everybody upset about the Big Crunch? Doesn't that bias how you see the problem? Or no, doesn't that bias how you see what's there?
Einstein was definitely biased. He wanted the universe to be static.
Yeah, well,
And so he engineered it to be static in 1917 by introducing the cosmological constant.
but you repeatedly said that this scientist or this person, the downside for this person or that he was Russian. Those are essentially like this idea that everybody is worried about the Big Crunch.
Or the Big Bang.
Or the Big Bang, but they're not looking for what is there, they're looking for what some idiom got them to launch, which is whatever their thesis was. And that biases what you're looking at.
So you have Edwin Hubble, 1929, coming up with this expanding, the recessional velocities being greater and greater the further these things are away from us, right? And that leads that additional support to the idea that of an expanding universe and a Big Bang in the past.
Yeah. And those are presumptions based on his path of assumptions.
Well, he has observations, and his observations are the further away the galaxy is, the more redshifted their light is.
Those appear to be less biased. But isn't, if you're out there looking for something and you don't find it, as opposed to you're out looking to see what's out there, is a very big difference.
Well, I think astronomers have been looking for a lot of different things.
Yeah.
They've made a lot of different observations. And over the years, they've been able to correlate a lot of those with things going on with general theory of relativity. For instance, in the 1970s, you have astronomers observing a lot of binary pairs. Some of them have a neutron star rotating a regular star. And the neutron star is very, very dense. So dense, like a tablespoon weighs as much as Mount Everest, right? It's so dense. And they start stealing mass off of their binary pair. Right? And as they point these X-ray telescopes towards these binary pairs, they can see the accelerated mass, which emits X-rays, going towards the neutron companion, and then they can see a splash. But there are also binary pairs where the companion is not visible. And they think that the companion is a black hole. And they too can steal mass off, and they can watch this same pattern of X-rays going towards the binary companion, but then it just gets cut off as it disappears
So
behind
those
the
appear
interest
to
of the
be-
black hole.
Those appear to be rather pure because they don't know how to interpret them.
Well, they do have an interpretation, right? They
Right.
think this is the matter disappearing behind the event horizon
Right,
of
so
the black
they give
hole.
it an interpretation. But the point I'm making, if you go after something you're looking for 50 years, if it's not there, it's not there in 50 years. But if you go after what's out there, it would seem to me that you're not going to miss something as easily as if you have a preordained approach to what's there. Just that's my,
Do you not think that's happened? Is that what you're saying? You don't think that's happened?
what?
What you just said, that astronomers, for example, have not been looking, period?
No, I wonder because of the way this is structured.
Oh, that's a separate issue.
Well, that's the only issue I got.
No, okay. I mean, you gather the data you can gather.
That's right.
You don't gather the data you can't gather.
Right, but you do go out and look for things.
Yes,
And-
within the confines of your capabilities.
Yeah.
There have been, since the 1970s, people have looked at whole broad classes of gravitational theories.
I mean,
Since the 1970s, people have, astronomers and scientists have had huge classes of different
Yeah.
gravitational theories, and they try to observe and see which one of these fits observational data, which ones don't. People have already been doing this for a long period of time, trying to narrow down the possibilities. We know that Newton's theory of gravity is not true. Einstein's theory of gravity is still the best we have. But there are non-Newtonian dynamics as well, and all kinds of different theories, adjusting little parameters here and there, and trying to see which of those best matches what we observe.
My big problem with you is, I'm impressed with everything you say, but you seem to be equating, you seem to be calling it a myth, everything that everybody's proposed, which answers it. You want to call it a myth, and you want to equate that to Genesis.
No, to me a myth has nothing to do with the connotation of being false. That's not what I mean by
Why
myth.
not just call it a theory that we don't have data for?
I'm just giving you the definition of myth that was given to me by my
I don't like that.
my college professors. You don't like that
I think
definition?
you're trying to equate that to Genesis.
Oh, you think I'm trying to
That
fit everything
seemed to
back to
be
Genesis?
the whole gist of what you did.
Well, not liking something is not an argument. It's an opinion.
I'll see if we have other questions. Did you have something?
Oh, I think my question's more just trying to clarify John's over there. I think you can correct me, John, if I'm wrong on this. I think what John was trying to get at is because of the way you structured the presentation, it doesn't seem like physicists have pursued the question of whether or not we can model a universe that does have a big crunch. Are there any models of the universe that do incorporate the idea of a big crunch, and have we tried to calculate that out and see if they hold?
Well, sure. There's the Friedman solution with the positive spatial curvature has a big crunch and a big bang. Big bang and big crunch. That's both.
why would anybody worry about the big crunch, which is kind of like worrying about everything?
What you're gonna have for
Once.
dinner.
It's gonna be there, it's gonna be there. It's like, why would you don't want the world to end? That's interesting.
Not gonna
That's
happen
the
in your
first
lifetime.
person that's ever said that. Huh?
It's not going to happen in our lifetime.
But I mean,
Anyone's lifetime.
of course, but it just, from a novice standpoint. It seemed that there was a bias in what they're looking for.
First of all, my apologies for being so late.
No.
I did my best. And you may have covered it, so please forgive me if you did, but. So, geometrical theories are considered to be classical theories, would you say?
Yes, and there are people who try to use theories that don't satisfy the usual axioms of Riemannian or non-Riemannian even geometries. In the 1970s, a lot of physicists became very frustrated because of these theories. And so they tried to find more general ways of analyzing things. But you're still stuck with certain kinds of what were called connections. And those are also part of these kinds of geometries.
So the reason I'm asking is because when you think about geometrical theories like Einstein's is considered to be one of the last true classical theories if you ignore the quantum world. And I know no one knows the answer to this next question, but what happens if we end up with a quantum theory of gravity? How would that change some of the assumptions that we have?
You still have a problem with the time. It has to be a timeless cause. Time, it seems like whatever this quantum foam does, that somehow spawned off a universe or two or a million. It seems that whatever those theories are, they are not scientific.
So would that being gravity not, I guess, the ideas of the graviton
Well,
as a fundamental particle?
we did mention that in Guth's theory from 1979, his inflationary cosmology, where he tried to marry quantum theory with Einstein's theory, what he ended up with was an even bigger bang. The universe expanding very much faster than the usual Einsteinian. You would have a bigger crunch if the universe came to that.
So it was unpopular.
Well, there's no evidence of the universe collapsing. It's expanded, and it seems to be expanding at an accelerated rate. So it seems like the cosmological constant might be forcing the universe apart at an accelerating rate. So most physicists are working in a positive cosmological constant these days.
I know that one of the attempts also for grand unification has been string theory. And if you can, and the problem with string theory, it has zero empirically verifiable data because we just don't have the technology, but all we have to do is build a super collider the size of the solar system or something like that.
String theory is all.
I was worried it was going to be something hard.
String theory does suffer the problem of having a large number of parameters that are not determined by the theory. So there's a lot of fine tuning you have to do in string theory. And so that's one of the reasons why they've had trouble finding these various particles that might be predicted by string theory is that they don't know where they are, what the masses are of these things, because those parameters are not determined by the theory.
Yeah, and I know it has been described sometimes as almost a religious-like theory because it has no empirical support.
Zero.
It just
Not a
fits-
single observation.
Not a single observation. And
That means that all the things that have been proved wrong, that the data didn't support, were just myths. That's the way I'm reading what you said.
What I said was a myth is a theory of origins. That's what I said. That's what I was told when I was in college. That was a long time ago.
Must be true.
Must be true.
Must be.
well, modern science was born out of the world of natural philosophy, so we did try to look at not just the empirical, but the very origins of modern science. So myth fits right into that really nicely.
All right.
So Jeff, the bias that you were kind of describing in your presentation that possibly some scientists have, are you saying, or maybe implying that the bias comes from the fact that if there's a big bang or something like it, that it basically means there are some things that we can never understand through science, and that's why that's not a way that scientists want to look at the world, that they always want to believe we can always continue to learn and grow, but if we believe there's something like a big bang, then there's a boundary we can never cross beyond, that's why we can't accept that theory?
No.
No.
I see a resistance in the audience to this idea.
No, I'm not asking what their opinion is.
Right.
I'm saying, is your implication, and that's,
I agree.
My implication is that we go back far enough, we can no longer see any light evidence beyond that barrier. There's no gravity waves that are primordial that have been measured through fog of that earlier time. There are no neutrinos measured from that earlier time. There are no observations, there's no data. And the theories that we have indicate that you can't even have a time earlier than that Big Bang. And that goes to even the theories that were developed in 2003. Right? So those theories, the most general singularity theorems that we have, apply to all of the gravitational theories that we have, even those that are not geometric, as long as they have this Lorentz kind of metric, some kind of metric that allows light to behave like light, then singularity must exist. So something has to fail if you want to try to extend things any further back, but it seems like time has that, there's no continuous way to extend it. So whatever that is, those come together in all theories, including this 2003 theory. Time can't be extended any further back. And so there's no hope of finding anything earlier. Okay.
Until we get further information.
So you want more data and more
No,
observations.
I'm just saying,
Scientifically.
but correct me if I'm wrong though, but the thing is though, what
Someday-
you're saying though is
there may be some.
there's only certain things, we're
And we say,
measuring
boy, were we done.
electromagnetic radiation. And you're saying that the electromagnetic radiation, we don't, unless we find some other, something in the universe that we can measure, that based on what we know about electromagnetic radiation, that we can't go further back prior to
That's
a
that
certain
veil.
point.
There's a veil that you can't see.
Yeah.
The only thing that might penetrate the veil would be gravity waves. But there's no observations of primordial gravity waves.
Yeah.
Yes.
Yeah. Okay. I'll buy that. But even
I'm
so,
hearing things in this room that sound as if it were 1902.
well, even if there were these gravity waves, the theorem from 2003 says you still have the time and completeness backwards in time.
But there might be some other force, some other concept, some other existence of some real, we didn't have bosons very long ago. And nobody worried a lot that we didn't have bosons, but once you found them, you said, so that's it. Well, maybe it'll be 50 years from now, or maybe it's next week.
Well, I
I
can
mean,
tell you this.
I just take this kind of, oh, we're lost, we'll never see something better, kind of vibe I'm getting in here.
Oh, no.
Science is always going to find something.
We'll get new tools. and
We
new
might not be
observations.
here, but science will keep progressing.
Yeah.
But not by people who are kind of not fully there.
Maybe something even smaller than what we know
Absolutely.
that's happening inside that Big Bang.
Who knows?
We don't have another particle or another force that we have not understood.
Absolutely.
Like I said,
That's
it would have to go
possible.
beyond all known physics and mechanics.
But
That was in my
fortunately,
talk. Right?
we have physics and mechanics today that we did not have 100 years ago. Maybe it'll take 100 years ago to get to the physics and mechanics that tell us something else, but maybe not.
The theorems are getting more dire since 1964, right?
Yeah, but then you wake up tomorrow and say, oh, I see.
You hope. You're holding on hope.
Doesn't matter.
We could also just be living in a simulation and it doesn't matter at all.
Yes.
Oh, well, there we go.
Well,
We're in the matrix.
Yeah.
It's a simulation.
So
And so does that.
the only problem that I keep seeing is he says it's impossible. Nothing could have been before. So the only answer is what Genesis says. But you won't say that openly.
I won't say that openly. Well, I'm saying that is a hypothesis. And it has explanatory power.
Genesis.
Genesis.
Yeah, that's what you're getting closer to what I think you believe.
Well, doesn't matter what I believe. I'm just presenting the history of the Big Bang. This is what has happened.
But you've twisted it with your definitions
I
to
did.
lead to that conclusion.
All right, well, I just want to thank everybody for coming. Next week, we have Mark Whitten, who will be presenting What is Humanity's Primal Problem, a Vedantic Answer. So thank you very much. Thank you, Jeff.